PADS Professional is a complete design suite for the single engineer or small design team. As an engineer, you're being asked to put more functionality into design, which in most cases requires additional circuitry, and with today's miniaturization, possibly being asked to put it in a much smaller space. Let's see how PADS Professional can help solve these problems. Let's start out by taking a quick look at the mechanical design of this smart drill. The mechanical engineer has created the board outline and placed critical mounting holes and components. We'll come back to this in a minute after we look at the schematic. To make your job easier in selecting components, we're going to use a component information system that is tied into either a corporate database or engineering database to make part selection much easier. In this case, the engineer needs to add a voltage regulator. So in the manufacturer part numbers column, we're going to type in the part number we found for the device we want to use and see that there's already a part in our database. We can now either drag from the row that's already selected, or we can go over to the symbol preview and drag that onto the schematic and place it in the proper location. We can now proceed with connecting this part to the existing nets. Using our right-click Draw Net function, we can quickly add 3 nets to this regulator. Next, we need to add the voltage adjustment resistors. This time we'll use the value column in the resistor table and type in the values of those components we need to use to get the proper output voltage. Just like before, you find the part, we drag it onto the design. You'll notice as I place parts in the design, there's alignment markers that show when I'm lined up with another component. This allows us to create a clean schematic from the beginning. Next, we want to reuse some design content from another project. So with that project open, we'll expand out the block section, right-click over the circuit that we want to use in our current design, choose Copy. We'll go back to our current design, right-click over the block section, and choose Paste. The symbol for that block is copied over with the schematic, so now we can go to the Library tab on our Databook window. From the Local Symbols section, we'll find that block, and we can now drag it onto our schematic. Using Designer's multi-net connection function, we can quickly connect up the nets between these blocks. With further automation, we can right-click over a block and choose Add Net Labels to connect the nets. We'll double-click into the battery protection circuit and see everything carried over from the other project we copied from. And then we'll review the last 2 blocks to make sure everything is completed. The next challenge I have is to verify none of the nets on my board will have signal integrity issues. Let's go to one of the nets that we might have a concern with. So let's right-click over one of these LCD display nets. From the menu, we'll choose Hyperlink's Line Sim. This will push the net into Line Sim and create the schematic with the proper models. Because I pulled all this part information from our component database, the proper models were assigned. We can now simulate that net by opening the oscilloscope. We have the option to check a rising or falling or oscillating signal. In this case, we'll set the frequency for an oscillating signal. We quickly notice there's a lot of ringing and overshoot. To solve this problem, I'm going to go ahead and add a series resistor. This will slow down the edge rate and reduce reflections. Now I can manually set the value for this resistor, or I can let the tool calculate it for me. So we can see the tool has chosen a 43 ohm resistor based on the impedance characteristics of our driver and receiver and the board stack up. We'll go ahead and simulate again and see that the resistor has done what it was supposed to. It reduced the noise and overshoot. In addition to adding passive components, we can also adjust the board stack up and see how that affects our signal quality. So let's go ahead and adjust some of our dielectric layers and move the ground planes closer to the external layers. This should help reduce the impedance of our traces and therefore improve the quality of the signal. We can now rerun the termination wizard just to verify if our resistor is still correct. And in this case, due to the impedance change of the trace, the resistor needed to change as well. We'll again go ahead and simulate, and notice with the 30 ohm resistor, we still have good or better signal quality. We can even compare it against our first run. So now we need to go ahead and add this resistor to our design. I've already done a search and found that we do not have a 30 ohm resistor. So let's go to PartQuest and find the part that we want to add to our design. From the search bar, we can type in a few parameters to find our part. You can see we quickly found a resistor that meets our requirements. You'll also notice next to the graphic of the resistor that there's a symbol, a footprint, and a 3D model we can use in our design. We can go over and click on the More button, view additional properties on the part. We can also add this to a project. This gives you a place to store component information for an entire project, making it easier to find the part for additional information. Let's stay in PartQuest and search for another part that I need in our design, which is a current sense resistor. We search through the results and we find the appropriate component, but we will quickly notice that there's no symbol or footprint assigned to this device. we have the option to create those items in PartQuest. So we'll go ahead and click on Choose Footprint, then Create Footprint. Walking us through a guided process, we'll start out by choosing the package type template that we're going to use for this device. We'll go ahead and choose Discrete, set a couple other options, choose the package shape, and then go ahead and proceed by entering the physical package dimensions found on the datasheet. When done, we'll go ahead and click Continue to Terminals. This next step will allow us to enter all the physical information about the terminals. So we can choose the type, if the pin is castellated, where the pins are on the package, and then what axis we want the part to be built on. Lastly, we'll enter all the physical dimensions of the pins based on the datasheet. Moving on to further details, we can set the terminal number pattern, if there's going to be a polarization mark or not, and the package body material. And the last step, we'll move on to validation. This is where we can set the IPC standard for this component, whether it's going to be nominal, minimal, or maximum condition. We click Return to Search, and the IPC certified footprint will be built and added to our part. Returning back to our search page, we can now click on Choose Symbol. For symbols, you have the option of creating the symbol from scratch, or you can use a template. In this case, we're going to scroll down and find our resistor. Since we're using a template and we already have the footprint built, our pin numbers are there, we just need to assign them to the appropriate object on the symbol. Going back to our search, we'll see the symbol graphic has been added to the part. We'll quickly add this to our project. Heading back over to our project, we can now select the two parts in PartQuest, drag them onto our schematic. This will add the symbol and the footprint and the attribute information into our library. From there, we can select the part, see that there's a symbol and a footprint, drag that into the appropriate location, and see all the attribute information that carried over. Now that we're done with our schematic, we can go ahead and validate all the parts back against suppliers to make sure none of our components have gone obsolete or are not available for purchase. We do this by using the supply chain application for Designer. To initiate this, you open up the Settings dialog box, go to Supply Chain, and click the Login button. A browser window will pop up where you enter your credentials to log in to the service. Once the login process has completed, we can go back to our design, and in the supply chain section, we can choose suppliers that we want to validate our components against. In this case, we will go ahead and add microchip. When we're done setting up our suppliers, we'll go ahead and click OK, and this information will be stored with your project. After leaving the Settings dialog box, a supply chain tab will be added to your search window, where it will instantly be filled with information about the components in your design against the suppliers you have chosen. We notice there are components with green, red, and yellow markers. If we go ahead and place our cursor over one that's red, we'll see that it's missing lifecycle and row host data. Double-clicking on that row will open a window where we can see additional supplier information for that manufacturer's part number. We can select a component that has good units in stock and pricing, and then click OK, and that information will now be added to our project. If we go ahead and place our cursor over one that's yellow, we'll notice that this part has multiple matches. Again, double-clicking on it will open up our search window with supplier information. In this case, the part number we have chosen is one that's not available by any supplier at this point. In this case, to solve this problem, we're going to go back to PartQuest and search for a component with similar properties and package. Once found, we'll go ahead and drag and drop that part into Designer so it will be added to our library. Instead of deleting the part out of our design and losing the reference designator, we'll go ahead and replace the part with the new one. So we locate our part, we right-click over it and choose Replace. To find the part, we'll go to our Library Part tab on the search window. So we'll go ahead and choose our part and drag it up into the new part number location in the Replace Part window. Once that's completed, we just hit Replace, and then we can go check that component to make sure it has the right manufacturer and manufacturer's part number. To verify our new part against our supply chain, we'll go ahead and refresh the data on the Supply Chain tab, and notice that our new part number we just added shows up as yellow, meaning there's multiple matches. We will go ahead and double-click on the part and choose a supplier with available stock and the best price. From our supply chain window, we can also export a bill of materials with all the supplier information. Up in our toolbar, go ahead and click Export. Once complete, in the output window, we can click on the name of the file and it will automatically open Excel. With some quick formatting, we now have a complete bill of materials with manufacturer, part number, vendor, and cost information. Most companies like to create multiple products off of one electronic assembly. To make this easier, Designer has an assembly variant capability built into it. Once you've created your variant or variants, you will see one or more columns in the spreadsheet. To make a modification, you simply right-click over a cell and choose Replace or Unplace. Once your variant information has been added, it's useful to create documentation showing which components have been replaced or unplaced. From the toolbar in Variant Manager, we can choose Create Functional Variant Schematic. You'll now see a version of the schematic with the proper part numbers and if a component has been depopulated. From there, we can create a PDF of that schematic for documentation. You can click on nets and cross-probe between pages. You can also click on components and see all of the attribute information with all of the variant information as you see it in the schematic itself. Lastly, and probably one of the most important features of variant management, is being able to output a bill of materials for each one of those variants, or even do a comparison between them or the master schematic. Moving on, design rules are mandatory for doing a PCB layout. In many cases, it's much easier if you can enter as many design rules at the schematic level when you're thinking about your electronic circuits, or you've done simulation. So from Designer, we can open up the Constraint Management system, which is the same rule entry system you would use in the PCB layout. This allows us to create net classes, clearance rules that can be reused between net classes, constraint classes where we would put our high-speed requirements like length matching, minimum, maximum length, matching between groups, just to name a few. We can also create area rules, which give us the ability to control trace and spacing from one area of the board to another area of the board. In today's society, working remotely has become more and more common. As such, we need an easy way to share our design data between other engineers, those in your company, and also partners and suppliers. Pads Connect allows you to store your data in the cloud, but not only store it, but put it under revision control and allow other personnel access to that data. Once you've activated Pads Connect and logged in, you will now be able to upload a project. Once you've chosen a project, you will give it a name and you can give it a description as well. When you click OK, the upload process will start. Once it has completed, or anytime you open up Designer with Connect activated, you will now see a Pads Connect project panel. This will show all of the projects that you have access to. So we will go ahead and open up the hand drill Bluetooth project. Simply right-click over it and choose Edit Exclusive. Once the design is open, you have full control over the project. If anyone else tries to check it out, they'll only be checking it out as read only. So after making some updates and outputting a bill of materials, we will go ahead and check this project back in. To do this, you can go back to your start page and choose check-in, or we can close out the project and it will automatically do it for you. As part of the process, it will also auto-create a PDF file. During the upload process, you'll be able to add comments about the changes that you made in the project. Once completely uploaded, you'll see the new version pop up on your Pads Connect panel in Designer. We can also go look at the data now in a web browser. Once you log into Pads Connect, you'll be presented with all the projects that you have access to. If you click the Home button in the upper left-hand corner, you'll see all the recent projects that you've worked on. You can then click on one of those, and you will now see the schematic and the PCB if it's been started. If we go ahead and click on the schematic, it will open up the PDF that was created during the upload process. Again, the PDF will include hyperlinking between sheets, and it will allow you to see attribute information on your components. We close out of the schematic view. We can now go back and click on the BOM, and you'll see all of the bill of materials information. You or anyone else that has access to the project can also export the bill of materials if needed. Alright, we're now ready to start the PCB. So the mechanical engineer has done some work of creating the board outline, placing some mounting holes and a connector in a critical location. From Solid Edge, the mechanical engineer can activate Ecad Collaboration. This will open up the collaboration dialog box. Since we're starting a new project, the engineer will choose Baseline. Once chosen, you'll see all the parts that are going to be passed across in the ProStep file. Mechanical engineer can then enter a description if they choose. Once they hit send, the files will be created and the PCB designer will be notified. The PCB designer will now have the advantage of using the electronic data from the mechanical engineer to create or start the project. So by opening a 3D view, we can open up the MCAD Collaboration dialog box. We will automatically see the file that was generated by the mechanical engineer. If we go ahead and click on the preview button, we'll see a ghosted image of the printed circuit board, the mounting holes, and the connector. We'll go ahead and hit apply, and we'll have the board outline and all of our critical items placed for us. Using Component Explorer, we can drag groups of components onto the layout to do rough placement. Once the groups have been placed, you can select one and choose Arrange Components. This will disperse the parts for us to place individually. We can also drag out components from the group area. If you click on a reference designator and drag it into the layout, you'll see the component appear so that you can place it. As you can see, we're doing that with the FETs for our motor drive circuit. We'll go ahead and place a couple other components just by dragging them onto the design. Switching over to 3D view, we're going to place components using 3D clearances. As you can see, we can set up various rules to DRC against objects in 3D space. We'll go ahead and place this U2 part, and notice that as we place it underneath that heatsink that we imported, the part will turn yellow, letting us know we're hitting our minimum design rule. If it turns red, that means we have a collision. So when we place the part, we have confidence that we're not going to hit this mechanical feature. Another helpful feature when placing components is being able to do it in 2D but see it in 3D as well. So we can open up two different windows, and then when we move a part around in the 2D space, it'll move around in the 3D and vice versa. Using our split window, we'll use it to assist with placing our FETs and the mounting holes. We go ahead and grab the FETs and mounting holes in the 2D space and move them around. I can see them in the 3D space. If I get too close to the heatsink, you'll see it turn yellow or red, letting us know we have a collision. Now that we have the board completely placed, the mechanical engineer would like a version of the design to place in his mechanical model. So again, from our 3D view, we will open up the MCAD Collaboration. And this time we'll choose a proposal, because we only want to send over the things that are different. Doing so, and we refresh, we'll see all of the components in our list. We can then add a comment about what we did. Hitting apply, and the data will be created and the mechanical engineer will be notified. Just like when exporting, the mechanical engineer will open up the Ecad Collaboration tool. When selecting the collaboration file, they'll be presented with all the data that's going to be imported. You will have the option of deselecting items that you don't want to import. Because this information is created by Paths Professional and being imported into Solid Edge, all of the 3D models of the components will also be imported. After the updates have been made, the mechanical engineer can now save the model and go back to his assembly. They will now see a completed printed circuit board for viewing and inspection. With the placement process now completed, we can go ahead and start routing. We'll start by setting up some fan-out properties and fanning out a couple of our components to make sure the power and grounds are set appropriately. After using Sketch to place a couple simple nets, we'll go ahead and route these main nets in the middle to the LCD connector. To do that, I need to set up some design rules. I need to define two differential pairs, so we can interactively select the nets in the workspace and they'll select in Constraint Manager. so that I can define them as a differential pair. Next, I will need to define a minimum and maximum length for the LCD nets. With our rule updates completed, we can now go back to the layout and route these critical nets. So using interactive routing, I can click on one of the differential pair nets and start routing to its location, and it will automatically grab the other and pull it with it. I can now select all the LCD nets, use the sketch router to draw a path where the nets need to be routed, and the auto router will complete those nets in that location. With the nets routed, we can go ahead and auto length match all the nets. Once the nets have been tuned, I can select them and use the target length dialog box to verify that they've all been matched within my requirements. Moving on to the next section, I want to control the fan out on these capacitors, so I'm going to draw in a trace and a via. Once completed, we'll select the trace and the via and go ahead and use copy paste to add the remaining. Next, we're going to define our plane areas on the board. Using automation, we don't have to draw our plane shapes. With dynamic capability, we can just use the route border that we defined at the beginning of the design. On this layer, we do need to add an extra plane area for another net, so we can go ahead and draw in a shape, and then the dynamic capability will take over, filling in that plane area. We can make a quick adjustment, and it automatically corrects. The BAT- pin that we drew this plane area for is also high current, so we need to adjust the thermal connections to the plane. We can do that by selecting the pin and then creating custom thermals on the fly. Before we move on to manufacturing, I want to do some electrical verification along with additional DRCs. So let's go ahead and take a look at that LCD net that we did a hyperlinks analysis on when we were capturing the schematic. From the analysis menu, we'll go ahead and choose Export to Hyperlinks. This will create a complete model of the board and open it up in BoardSim. Once in Hyperlinks, I can select that net, open the oscilloscope, and do a verification. From the simulation results, it looks like we're good. Now that we've done our verification, we're going to go ahead and send a model over to the mechanical engineer so they can review the part placement and also do thermal simulation. Seeing we've been in communication with the mechanical engineer already, we don't want to create a baseline. We want to create a proposal which will only send the new content that's been added since we've started the layout. After performing a quick refresh to make sure we have all the right content, we'll go ahead and add a quick comment about what's being sent and create our collaboration data. Our mechanical engineer can now import the data we just created using the collaboration app from within Solid Edge. We can see the entire board imported with components and traces, but we don't quite see the plane, so let's go ahead and turn off the outer shell of the PCB to expose the internal plane areas. With a quick visual inspection, we can see all the plane data appears to be there. Switching over to the 3D view, we can do a quick visual inspection of the board inside the mechanical enclosure. Before we move on to generating manufacturing data, let's go ahead and take a quick look at PADS Professional's Rigid Flex option. To start this Rigid Flex design, we're going to import data using the collaboration interface. With our Flex and Rigid board outlines imported, we now need to define each one of the Flex area regions. We do this because we can assign different stack-ups per area. I've already gone ahead and defined the stack-up for this board, so you'll notice the cover layer, adhesive, and stiffener have been added already. So we're simply going to choose the layers that will be part of this LCD Flex area. If we go ahead and hit the View Stack Up button, we'll get a quick view of the layers being used for this Flex region. With our stack up areas defined, we can now go ahead and start creating our bend areas. To do this, we go to the Draw menu and choose Bend Area. We now create a rectangular shape that represents where that bend is going to be placed. From the Properties dialog box, we can set things like the radius, the angle, the width, where the bend area origin is, and other various settings required or that can be used for Flex design. With one of our bend areas defined, we can now jump over to the 3D view and see what our bend looks like on our Flex and how it fits with inside the mechanical drill housing. Before we move on to routing, let's see what happens if we place this resistor on the Flex. Pay close attention to the pad geometry that's being used on the rigid part of the board and what it looks like on the Flex. Notice how the pad shape automatically turned to rounded corners. If we go look at this in the 3D space, we'll also notice the cover layer is using rounded corner openings. PADS Professional handles this by adding special Flex pad stacks to the component. And when it detects it's in a flex area, it automatically swaps out the standard ones for the flex ones. Now we can go ahead and route traces from the flex fingers up into the printed circuit board. To simplify this process, we're going to use a feature called multi-hug trace. As you can see in the tooltip video, this feature can use other objects as a template to draw your traces. So here we're going to use the flex outline as a template. With only a few clicks, we've added all our traces. Now we can complete the finger to the trace with a couple simple routes. With our routing done on the LCD flex, let's go ahead and add the stiffener now that's going to be required in order to mate this flex with its connector. We'll turn on a drawing shape that we've had off previously. We can then select the shape that was already there, turn it into a stiffener, and now it will be represented as that when we look at it in the 3D view, and when we output our documentation. Before we move on, let's go take a quick look at the design in 3D. So we'll turn on bends, and we can see how the flexes are currently formed, and then we can turn on the housing of the drill body to visually see how everything fits. Alright, we've come back into work after checking our design the night before, so we need to check the design back out, and we'll finish our DRCs up and go ahead and output our fabrication data. From the main toolbar, we'll go ahead and activate our batch DRC. You'll notice that it'll already come up pre-configured because for our batch DRC function, like many other features within Paths Professional, you can create schemes so you're not having to readjust everything on the fly. After performing our DRCs, we're now ready to output our fabrication data. Instead of using Gerber, we're going to go ahead and output ODB++. This file format creates an intelligent database for fabrication and assembly. With a quick review of the data we're going to output, we'll go ahead and create our content. With Paths Professional, we can review the data after it's been exported. So we've turned on the ODB++ viewer, which will load the data that we've just created automatically. With the ODB++ viewer, we can turn layers on and off to see exactly what our fabricator is going to see in the end. And if you still like to use Gerber, this viewer offers a ODB to Gerber comparison to show you that the Gerber data has exported exactly like the ODB++. Now that we've exported our manufacturing data, we'll do a manufacturing check using Siemens PCB flow. So from our project overview tab, we'll click on Create Project, and we'll give this a name. You can give it a description as well if you like. We continue on to the next step where we'll import the actual ODB content. So we upload our file. So just take a second to upload the data. We can then do upload and continue. Next, we're going to choose a fabricator's design rules that we want to verify our design against. In this case, I'm just going to use our test one here, PCB flow. Then hit Run Analysis. PCB flow is free for any customer that creates an account, but with limited reporting capabilities. If you want to expand your reporting capabilities, you can purchase a subscription. With the analysis now complete, we can click View Report. A new tab will appear with all of the report information. To filter through items shown in the main part of the window, we can click on Layers and then Constraints. Let's go ahead and click on Layer 1, and then from the Constraints drop down, we'll click on Plated Through-Hole to Plate. So here we found a warning, but not an error. We know that because this yellow triangle that's showing up here at the top. If it was an error, it would show up as red. We can see the actual measurement that the tool found, and then down below here we can see the design rule in which it's checking against. Because it's below 10, which is preferred, but not below 8.5, this is just a warning. If you want to know more about any one of the constraints that you select, you can hold your cursor over the I button, and it will give you a complete description of what that verification is checking for. If we want to navigate back to where this error is, it gives us the exact coordinates of where that error is occurring. So we can click on this icon here. This will copy those coordinates, and then I can go back over to Paths Professional. We'll zoom in, and then we can use the ZC key-in command, paste in our coordinates, and we just need to put a comma and get rid of that space, hit enter, and it will take us to that exact location that the DFM report is showing as an issue. Now again, this was not a design rule failure, it's just a warning. We can also export a report that we can email to colleagues. or to keep with our records for this design. Once our report's created, we can go ahead and click on that and review the DFM content. I sent my colleague an email letting him know that I've uploaded the content and he can go review it. Once signed in, you'll notice he doesn't have all the same icons here on the left because I've only assigned him viewing and DFM run capability. He does have the capability to review the design real time instead of looking at the PDF. Since my colleague will be the one that's going to be making the changes, he can review anywhere where we have violations, copy the coordinates, and go back over to PADS Professional, and then find those locations and make the update. So after my colleague has made adjustments to the design, they can then go re-upload the new files by using Replace File and redo the verification. Now that we're done with the design, we'll go ahead and close the project. Because we associated this project with PADS Connect, it will automatically activate two functions, generating a PDF of all the layers and creating a 3D output of the design. Before we complete the check-in process, we're asked to add a comment to document what we did while we had the design open. The check-in process will now bump the revision, add all of our design content, along with the PDF and 3D output that we generated. Let's go review the data that we've uploaded into PADS Connect. When we click on the board file, we'll be given a 3D view of the PCB with all the flexes in their final bent positions. As we've seen, PADS Professional provides a complete design suite for the single engineer or small design team, which includes schematic capture, analog simulation, signal integrity, stack-up design, supplier integration, design data management, team collaboration, library automation, placement and routing automation, collaboration with MCAD, and 3D design. To quickly discover the power of PADS Professional, you can also participate in our cloud trial, which includes the following labs: Complete Design Overview, Rigid Flex Design, HDI Advanced Routing, and RF Design.